You can approximate reaction enthalpy using Hess's law and tabulated bond enthalpies. Now, I haven't talked yet about Hess's law in these lessons. That's a topic for another day. All you need to know to approximate reaction enthalpy is this equation, which I've simplified to be broken minus formed. If you tally up the bond enthalpies of the broken bonds and subtract the bond enthalpies of the formed bonds, that will give you a pretty good approximation of the reaction enthalpy, and will then tell you whether the reaction is exo or endothermic. The reason that the formula is broken minus formed is because whenever bonds are broken, you have to put energy in, which that means that energy will have a positive sign. Whenever bonds are formed, energy is released, and that has a negative sign. So that's why we have this equation, broken minus formed. Let's try an example. Let's approximate the reaction enthalpy for the combustion of propane. This is the fuel that is used in gas grills whenever we're grilling hamburgers or so on. Propane has that formula. If you knew that, great. If you didn't, it's okay. I'd be happy to give that to you. But you should know how to figure out the rest of the equation. Combustion refers to the other reactant being oxygen, and we're supposed to know that any time we have complete combustion of a hydrocarbon, we're going to get carbon dioxide and water. Then we need to balance this. I trust you can do that. What we'll do now is draw the Lewis structure for each of these different substances. There's propane. Oxygen is most easily represented this way. Water and carbon dioxide. So then what we need to do is find the bond enthalpies by looking them up. And we are going to break two carbon-carbon single bonds, and I'm going to use my laser pointer right there. There's a carbon-carbon single bond, and there's a carbon-carbon single bond. So we need to break two of those, and I've looked up the bond enthalpy, and it's 348 kilojoules per mole of carbon-carbon single bonds. Similarly, we need to break a total of 8 carbon-hydrogen bonds. Then we need to break a total of 5 oxygen-oxygen double bonds. You can see that I've drawn a picture and there's only one double bond there, but there's a coefficient of 5 in the equation. So we actually have to break 5 of those, and the bond enthalpy is 495 kilojoules per mole. Those are all the broken bonds. If we tally that up, that's 6475 kilojoules. Now, let's do the same for the bonds that are formed. And so what bonds are we forming? On the product side, we have oxygen-hydrogen bond, and there's another one 4 times over. That's a total of 8. Again, these bond enthalpies we have looked up in some reference source. We have 6 carbon-oxygen double bonds. Those are the bonds that are formed. If we tally those up, and then we go broken minus formed, the number that we get is somewhere very close to negative 2000 kilojoules per mole, which would suggest that the combustion of propane is exothermic because of the negative sign. And in reality, the reaction enthalpy for the combustion of propane is about 2200 kilojoules per mole. This gives us a reasonable approximation of the reaction enthalpy.